Let me get the things going. First of all, this is the presentation outline. We're going to give a very brief introduction, say why we do this balance mix design and the QC/QA framework. And before we do that, we're going to talk about the current practices for BMD and the QC/QA, what the concerns are. And then we're going to present the Coherent framework for BMD and the QC/QA. And with this in framework, we talk about the 4 pillars of this Coherent framework: volumetric design, performance evaluation, performance verification, and QC/QA. Specifically talking about the 2 sets of lab tests for performance evaluation and QC/QA, and also verification. And we additionally, within this framework, we have to discuss another 2 very important aspects. Is about the aging protocols. We're going to give very detailed, specific aging protocols for different pillars. And then we're going to present one example to demonstrate the whole process. So we not just give you a framework without any details. And when you have see this demonstration example, you can duplicate what we did through this process. Finally, give a summary and a conclusion. Again, introduction here, talking about practice for balance mix design and QC/QA. Specifically for the balance mix design practices right now, most of DOTs, I'm thinking, they're using volumetric design, silver paper volumetric design, plus performance verification. And for example, many DOTs are using Hamburg or APA for evaluating rotting resistance. Some DOTs, like in Texas, using overlay tester for cracking resistance. Illinois DOT using the IFIT. Minnesota using DCT. I think Louisiana DOTD using SCB-JC test for cracking verification. But that's the current practice. This way, and the way, requesting the volumetric design plus this performance verification, we really not open up the opportunity for contractor, for designer, to, innovative designs, because we still limited the volumetric 4% air void to choose the asphalt content, then you perform verification. So that's really biggest limitation. We're trying to find an alternative way to give the contractor or designers the way to innovate their mix design. That's the one who goes this framework. In terms of the QC/QA practice, I think most of DOTs contracts are controlling 4 parameters: rise, dense, specific gravity, and also lab mode density. Another 2 is asphalt content and aggregate gradation from the ignition oven test. So then we have the concerns talked about here. The biggest concern is the balance mix design. We really talking about the performance test, but right now there are no performance test. Is run during the production. So that's there are no coherent connection between BMD and the QC/QA. I think that's the major concern. And again, I just already mentioned, the reality is performance test will ensure have good performance during balance mix design. But if we don't have any performance tests run during the QC process, we really don't know our mix produced is what we designed in the lab. So why there are no performance tests during the QC process? Because the current performance tests take too long to finish. So we all know the QC really require very efficient tests in order to be used during the QC process. So the consequences I already mentioned a little bit. at least the two consequences we're talking about here. The first one, what is produced at the asphalt plant may be significantly different from what was designed in the lab. So that's not what we want. We want with balanced mix design spend so much time and effort to come up a balanced mix with in terms of cracking and rotting and moisture damage. But when we're doing the production, and many things could vary from the original design. So the second one, we couldn't detect the binder sources change during production. Because the binder source change, from one, for example, 64 binder to another 64 binder, and you will not changing specific gravity or level mode density, even binder content, gradation, there's no change at all. But due to the binder sources change, you could lead potentially rotting issue and cracking issue. That has been happened in the past, been reported by many contractors and state DOTs. So that's really the issue between the BMD and the QC/QA. So the second one is about the aging protocol. And I think most DOTs are following the R30, the AASHTO R30 aging protocol. Basically, they're talking about the 4 hours at 135C for performance test, for rotting tests, and that's most people using. So, but 4 hours 235 at 135C is really too long for QC, but maybe it's too short for cracking evaluation. So what we really need is a proper aging protocol fit best for both BMD purpose and the QC/QA purpose. So that's the two major concerns with current BMD and QC/QA process. So the objective of this presentation of this work we did before is establish a coherent framework considering both BMD and QC/QA. And again, I mentioned this QC/QA and this framework has 4 pillars. And we really talk about the volumetric design component, performance evaluation component, performance verification component, and the QC/QA process. It's supported by 2 sets of performance tests and associated criteria and the 2 sets of aging protocol. Again, we're going to have a demonstration at the end of, closer. This is a real project, a real project we during our have the accelerated payment test section construction in Texas. So that's what I'm going to talk about. And let's, when we tried to establish the coherent framework, and we consider the different aspects or different requirements, different constraints. Again, the goal is trying to get both BMD and the QC/QA are coherently connected. And also we need to consider performance tests for the QC/QA as well. So that's the overall goal. We want these things efficient and effective for both BMD and the QC/QA. And the second consideration is about the air void issue. I mentioned a little bit, before, the air void in the past before SuperPave, can vary from 3% to 5%. That's a common practice for Marshall design. So, but since SuperPave, everybody using 4% air void to choose the optimum asphalt content. But really, the air void could be very. Even in this study, we're going to explore between 2% to 5%. So we're going to talk about it later time. Another thing is about the time constraint issue. We all know when we design a mix in the lab, and it could be done in weeks or months. Really, the time-consuming tests are okay for mix design. But we all know for the plants at the QC process and for the plant, we have to complete the QC test within an hour. We're really talking about hours. So in that perspective, we really emphasize the test must be efficient, at the same time effective. So that's really the time constraint. That's why we're talking about 2 sets of a test. And at the same time, the aging protocol as well. Again, for the QC as for the plant, really talking about short-term aging. We can't afford to do long-term or even mid-term. We talk about later time. So that's the different set for the, again, during the mix design, again, we have the enough time to do a good mix design. We can, consider both short, mid, and long-term aging. And specifically for cracking, and we have to talk about a little bit longer term than short term. We're going to go a little bit detailed later time. So with this different aspects, we present this coherent framework for balance mix and QC/QA process. Again, it's a four pillar. You have four pillars, and we start from the raw materials, and we have the aggregates, asphalt binder, you have wrap, you have shingles, some duty still allows shingles. You can add your rejuvenator, any additive. That's really talking about the raw materials. After you blend all the raw material together, let's move to the first pillar, volumetric design. We're talking about the short-term aging here. That's really our acetal R30. Short-term aging is 2 hours at compaction temperature, and you compact your specimen with super pale gel to compactor, and then you get this air void versus asphalt content, and then you can choose. I really recommend 3 asphalt content, not just one asphalt content at 4% air void. We're really talking about the lowest air void or the highest density, the 98%. We really don't want to go beyond 2% air void, lower than 2% air void, or denser than 98% density. Because beyond the 98% density, you potentially not just rotting issue, you potentially cause bleeding issue. So 2% air void is the upper limit. Give me the optimum upper limit for asphalt content. I don't want to go beyond that. So that's the volumetric requirement. Don't want beyond or below 2% air void. And at the same time, you choose another. You can choose 4% or 3%, then 5%. You get 3 asphalt content. That's what we say from volumetric design, you get 3 asphalt content. Then you move to performance evaluation with these 3 asphalt content. Again, this for short-term aging. Again, short-term aging. And we're just trying to find very efficient and also effective performance test because we are dealing with multiple asphalt content. We don't want test takes very long, so we want very efficient, effective test. And this same performance test is going to use for the QC/QA. So that's how they connect between performance evaluation with the production. Okay, but after this, 3 asphalt content, you mold your specimen, you run rotting tests and performance cracking tests. This what's happening here. This is the graph is about. So the left hand, that's my rotting. Always rotting is the top priority, and then the cracking as well here. And for this right line, and this is the rotting resistance, your higher asphalt content, your rotting resistance become lower. And for the cracking, this in this line, the higher asphalt content, the better cracking resistance. And then you have this criteria for the rotting test and the criteria for the cracking test. Then you got your balance zone here. So when you use this balance zone, you can choose asphalt content, choose one asphalt binder content, and for further verification. Because this we use pretty fast, efficient, effective test, but most of the DOTs, for example, when they pick up a rotting test, they're either using Hamburg or APA, and that's not suitable for this test. Although you could do it, but take pretty long time to finish this part. But this performance verification at one asphalt content really give you users you can prefer the performance test. If you prefer your Hamburg test, this is a chance to verify your asphalt content. I call balanced asphalt content. From in this zone, you pick up one, you further verify it. And the most critical one for here is you can consider the aging time, especially for the cracking. And you can consider mid-term aging or long-term aging for your cracking test. So that's how the beautiful thing for performance verification, you can use your preferred performance test, and at one asphalt binder content, and at multiple aging conditions. If some people want to run some IME performance analysis, this is also opportunity as well. You can run your performance analysis through this stage. And again, after you run this test, run your preferred test, and look at the performance criteria, because we're not just talking about short-term aging, we're really talking about for cracking, mid-term aging, or long-term aging. So the performance criteria is different. So again, this one asphalt content, if they pass these performance requirements, then you move to the production trial batch, or the QC/QA. Again, we're talking about short-term aging, and is sublot basis, QC, Q test, QA test plan, and the criteria. Just, again, this is the 4 pillars: volumetric design, performance evaluation, performance verification, and production QC, QA requirement. So this is the whole system we really talk about right now. That's how we call coherent framework. So everything coherent, connected, in terms of, not just step by step, is also in terms of lab testing, aging, all how connected. I'm going to give more details step by step. So the next step, and as we mentioned, we really need 2 sets of lab performance tests and also criteria. And the lab tests for performance evaluation and QC/QA, we really emphasize efficiency and effectiveness as well. But for the lab tests for the performance verification, and really DOT can choose their preferred test. Like Texas, you can choose your overlay tester. Illinois, iFit. The Louisiana, you can choose your SCB, JC. Minnesota, they're using the DCT. So this is a really good part for performance verification. And also, again, for aging protocol, for short-term aging, really, trying to address volumetric, performance evaluation, and the QC/QA, because the QC/QA really needs both volumetric, talking about the rise value, and also performance evaluation, my routing test acceptance, routing test criteria, and also cracking test criteria. So all these 3 really talk about short-term. And we introduce right now to talk about mid-term aging. I'm going to give you more detail, specifically for cracking performance verification. And when we talk about aging protocols, we give more detailed information, talking about why we choose that, and what's the benefit when we choose that. So this is the next several things, slides under this coherent framework. We're talking about really performance test and aging protocol and criteria. So that's 3 major things we have to nail down. Then we move to the performance test. When we're talking about performance test, we really have 5 aspects to consider. And we're trying to address the 3 major distresses. And we're talking about rotting, cracking, and never forget moisture damage or stripping issue. People always talking about rotting, cracking. Our performance should be beyond rotting and cracking. We have to consider moisture damage. And the same thing, and the second aspect, we want the same lab test for both performance evaluation and QC/QA. So that's very important. And in this such a way, we can connect these 2 and become a coherent, coherent framework. And we're really talking about effectiveness as well, not just efficiency. We have to make sure any performance test we select or recommended going to have good correlation with field performance, talking about good performance with cracking, rotting, and moisture damage. And also we're really talking about simplicity as well. Simplicity can, talk about the operation, a test, how simple and to run the test, and also the sample preparation. How do we involve so many cuttings, gluing, and instrumentation, all this stuff. So we really emphasize simplicity and also efficiency. We don't want tests to run several hours. Surely in some areas for the performance verification, yes, no problem. But for the performance evaluation, specifically for the QC process, we really want this test to run very efficient, hopefully less than, talk about minutes. So that's when we talk about field performance tests, that's we consider these 5 aspects. So I think you all probably very familiar with this performance test for 3 categories: cracking, rotting, the stripping test, or moisture damage test. I have 9 cracking tests I only listed here, probably more than this, but this is the 9 cracking test. Has been, in the last 10 years, either evaluated by NCHRP 957 or 957A, or FHWA is working on this one, the last one, ISO-TP 107, AMPT cyclic fatigue test. So again, let me quickly go through this. The first test is ASTM D7313, that's a DCT test. And the second one, that's the SCB low temperature, it's ASHTO-TP 105. And the third one, that's ASTM D8044, that's SCB-JC. The fourth one, that's the ASHTO-TP 124, that's the Illinois Flexibility Index. And we do have the IDT, Florida, University of Florida method. We have a Texas overlay tester. Some people using bending beam fatigue test, that's ASHTO T321. We have the ideal cracking test, or ideal CT, the ASTM D8225. Similarly, we have 9 cracking rotting test, Marshall stability test, Hamburg well tracking test, APA, and flow number test, and the Silverpave simple shear test. I think this test only right now is UC Berkeley can run this test. And we also have the ASHTO-TP 116, that's called PID test. Also have the TP 134 stress sweep rotting test, and we also have a high temperature IDT test, and also ideal RT test. And in terms of the moisture damage, I think the 2 tests that people are still using, either using TSR test or Hamburg whale tracking test. This is a test, common test, around available to choose. But when we choose simply, several tests here specifically for the performance evaluation, the QC/QA. For the cracking test, we choose ideal cracking test. For the rotting test, there are 2 options here: ideal RT and or high temperature IDT, because this test is really simple and have pretty good correlation with field performance. And for example, the ideal CT has been validated by many field test sections for fatigue, cracking, for refractive cracking, for top-down cracking. For the ideal RT and the high temperature IDT, all these 3 tests, you just mold the specimen, then you test it. No any instrumentation, you just so simple and very efficient, effective test. That's what the performance evaluation, the QC/QA preferred or mandated. You have to, in order to get using the QC test, that's the test we recommend. And for the performance verification, for the moisture damage, you can choose either Hamburg or TSR. And for the rotting test, again, you can choose Hamburg, APA, or any other test you prefer. For cracking test, again, you can choose any test. Ideal CT, OT, IFIT, SCB-JC, or bending beam fatigue, cyclic fatigue, DCT, or any other test. But again, for our recommendation, this paper or this presentation, we focus on 3 tests. And again, for the ideal CT and RT for performance evaluation, and also for QC/QA. And we choose Hamburg test for an ideal CT for performance verification. So simply, we only choose 3 tests. And so we have the confidence to use these 3 tests for really, a balanced mix design, and also QC/QA. And so after we choose this test, the next very critical thing is about the aging. And how can we age our mix? And because aging really close tie with the performance acceptance criteria. Without a specific aging protocol, I can say, we can easily pass any criteria. For example, if I want to pass my rotting test, I cook my mix in the oven longer time for rotting. if I want to pass my cracking requirements, I cook my mix in the oven less time. So that's so critical when we talk about any acceptance criteria. We must specify corresponding aging protocol. Again, when we talk about the aging protocol, we also talk about the 5 aspects here. The number one is a reality thing. We need to check. Every year we talk about million tons of mix in each state. What all this mix be useful? And I did some literature search. What I found, at least 75% asphalt mix is produced every year used for asphalt overlays. So that's very important. And if we really want to talk about our practical application, we really need to look at asphalt overlay mixes. In terms of these asphalt overlay mixes, how they perform in the field. I look at the literature, is 90% our overlays and cracked within 4 years. I'm really talking about significant amounts of cracking, because when we talk about asphalt overlays, most of the overlays is less than 2 inch. If we, based on the rule of thumb, we talk about 1 inch per year, you easily say, within 4 years, most of them you have already cracked. So that's something, this study, which when we developing the aging protocol, that's the things in our mind. We're really trying to address asphalt overlays. The reality overlay only lasts less than 4 years. So the second thing, when we talk about aging, really aging has 2 completely different process. The first of all is during the production here, and also talking about transport and the placement. And in these 3 areas, we're talking about asphalt mix very at high temperature, and talking about relatively compared to years of service. Here we're really talking about short term. So here we're talking about short term and high temperature. That's what we have to address when we're talking about the aging protocols. Meanwhile, after this placement going to service years, we're talking about much lower temperature than during compared to the construction, and a much longer time. So we need to address both during production, placement, and also the long-term performance. And another thing we have to consider, I mentioned before, is our mix rotting the cracking resistance. It varies with the aging or time in opposite ways. And the longer you aging the mix, you have better rotting resistance, have poor cracking resistance. So we have to consider this when we choose critical aging times. So we need to choose the rotting. We need to talk about short-term aging, and that's the most vulnerable time for mix potentially prone to rotting. For cracking, we have to age it a little bit longer time. So that's the time. That's why we need different aging protocols. Again, we need different aging protocols for balanced mix design stage and QC/QA, because the QC part, we only have an hour we talk about. We really need short term. We cannot afford to do long term during QC process. But the BMD, you have time. Yes, you can do it. So again, the aging specifically for aging protocol, we're really talking about aging, how long we aging the mix. We're talking about duration or time. We also need to specify the temperature. What's the temperature we need, cooking our mix in the oven? And then it's more than this time and temperature, we have to specify our loose mix thickness. We're really talking about 2 inch, 3 inch, or really talking about 1 nominal maximum, aggregate size. So all this is different. So we have to specify all this information when we talk about aging protocols. Again, in the literature, all sorts of aging protocols exist. I don't want to go these things very detailed, but basically you have very short-term aging. And in R30, we really have during the volumetric design, talk about compaction temperature at 2 hours. That's for volumetric design. And about most recent, in the last several years, the NCHRP 9-52, they really, find out really need 2 hours at 135 C. and for short term. And although for 4 hours at 135 C has been used for many years for performance evaluation, is also specified in R30. But based on all this, most recent studies, really it seems like the 2 hours at compaction temperature or specific 135 C for hot mix, that's the things really, for short-term aging. Again, for long-term aging, the R30 have the 5 days at 85 C, and another study, NCHRP 954, and recommended by Professor Kay in North Carolina State University, and talking about 1 day or multiple 24 days and for at 95 C. And NCAD recommend 8 hours at 135 C. Some people use 24 hours 135 C. So all different type aging protocol existing in the literature. So for our study, when we choose this, the aging protocols, we really trying to specify 4 different aging protocols. Really, we're trying to simulate the kind of plant production, the transport, placement. We're really talking about short-term aging. This is the short-term aging. And for the midterm, really, we define midterm 1 to 4 years for the field service. I just mentioned that's as for the overlay, you see the cracking is within 1 to 4 years. You see lots of cracking. We have to address that. And for long term, like in the PAV binder aging, really talking 5 to 10 years aging, they do 20 hours at 100 degrees Celsius. That's for the binder PAV. Most recently, NCHRP 9-60 talk about longer than 10 years aging. And so it's really have different aging here. But again, for us, and we focus on this part, the short-term aging and the mid-term aging. And this just illustrates the blue line, that's rotting resistance. In the beginning is pretty weak, this short-term, and then getting stronger and stronger. But this is the most vulnerable time for rotting resistance. That's how we say we prefer short-term for rotting, regardless during the performance BMD process or even the performance verification process. And so, but for the cracking, we need to consider short-term and also we call mid-term. Beyond the short-term, we really don't want to talk about 10 years because our cracked, most of overlays cracked with less than 4 years. We really talk about, here we call mid-term aging. So after review all this information, we recommend this aging protocol, again, for different stages, 4 pillars for volumetric. And we're really talking about short-term aging with 2 hours at compaction temperature. For mixed performance evaluation, for ideal RT, ideal CT, it's same thing, short-term aging, 2 hours at compaction temperature. And for performance verification during the mix design process, for Hamburg, and again, it's 2 hours at compaction temperature. And I choose Hamburg can address both for rotting and the moisture damage. That's the beauty for Hamburg. For the ideal CT, we really talk about the mid-term aging. We pick up the binder aging 20 hours at 100 degrees Celsius. This one, why we pick up this specific time and temperature, because 20 hours is the most practical time, and for 20 hours. If you go less than 20 hours, you really have lots of issues. And for example, like 8 hours or 6 hours, and how can you do that? 1 day, working day hours only have 8 hours. That's the cause of lots of problem. So that's why we recommend 20 hours. You just overnight, and second day you come and you compact your sample. For the QC/QA process, again, is matching 2 hours of compaction temperature. So you can see it's very consistent. We get 2 hours compaction temperature for volumetric design, performance evaluation, and the QC/QA, and also perform verification for Hamburg. But for only a little bit longer term, mid-term, we're talking about this ideal CT. So that's the beauty. This recommend framework and the protocol is very efficient in both testing and aging. And again, the next step is talking about acceptance criteria. And so we have the test, we perform the test, we pick up aging protocol. The next one is acceptance criteria. For RT, and we don't have the criteria yet, but for the CT, we do have the criteria is larger than 90 for this short term, 2 hours at compaction temperature. So always remember, when we're talking about the criteria, you always need to specify the aging protocol. And for the midterm aging, we don't know yet. That's we have to figure out. For the Hamburg, I think everyone, most of DOTs, when they're using Hamburg, they have their own criteria already. So we don't need reinvent the wheels. So that's how we have. The only thing we don't know is about RT, acceptance criteria, and the CT and midterm. That's how we did, for this study, we get 23 mixes, and including different binders, different wrap percentage, shingles percentage. So we have different binder content, you have different type silver pave and SMAs. And we run Hamburg and ideal RT, and we had this correlation. So based on this correlation and also existing Hamburg test results criteria, we came up this RT criteria for different mixes with different type binders. For mixes with PG6 falls, the minimum requirement is 60, and for 70 binders is 65. For 76 for mixes with 76 binders is larger than 75. So we have this RT criteria. Then the next one is going to be the CT criteria. We work with 6 mixes here, and both silver pave mixes and SMA. We have 9.5, half-inch and half-inch SMA. We have binders 64, 70, and 76. And we have different wrap and rest. Even we have one rejuvenator. We're trying to see how different mixes we age at different conditions, how this, changing versus aging time. This is a graph showed. This is a normalized graph, and we normalize all these conditions at 2 hours at compaction temperature, normalized to 1. And this one, that's 4 hours at 135. And this one is 20 hours at 100 degrees Celsius. The last one is 3 days, 72 hours. I'm sorry, it's 6 days and 144 hours at 95 degrees Celsius. And if you look at carefully, after look at normalization at 4 hours 135, we have big wide range of cracking resistance change. Some mix, and for this mix only reduced, on the 90% after 4 hours, still can retain 90% the 2 hours at compaction temperature CT index. But for some mixes, only have 69%. So we really talk about the big, more than 20% vary here. But if you look at the 20 hours, have the smallest standard deviation, and the average is 48% when we compare to the 2 hours at compaction temperature. When we age to 6 days, the standard deviation become higher. So that's why we finally choose just 2 hours, 20 hours at 100 degrees Celsius. It's matching the APA, the PAV binder 20 hours aging and 100 degrees Celsius. That's how we choose. We call midterm aging. And what's the percentage reduction from 1 to this one? The average is 48%. When we consider one standard deviation, that's 45%. That's how we came up with the CT index at 40. And you remember the 2 hours at compaction temperatures acceptance number is 90 times 4.5, 0.45. We got 40. So that's how we have ideal CT and midterm aging acceptance is 40. So with that, this already mentioned. Again, the RT requirement is here. the CT requirement, the short-term aging, CT requirement, mid-term aging, all we have this performance criteria. So that means all this framework is already established. We have the 4 pillars. Also, we have the performance test. We also have the aging protocol. We have the test acceptance criteria. So the next one, we're going to quickly demonstrate this process. And again, this half-inch silver pale mix and with limestone aggregate, the original binder, the virgin binder 70 metal 22. But since we use wrap, we substitute the virgin binder with this 64 metal 22. So the mix actually uses 64 metal 22 with 25% wrap. And this is the gradation here. So the first step is volumetric design. Again, we choose the original silver pale N design 35, and we have 3 asphalt content. This, you see the blue dot here, that's going to 4.5, 5, and 5.5. That's the 3 asphalt content we use for silver pale volumetric design. And for this 3 asphalt content, we got a different lab molded density or air void. And again, our maximum density is 98 or 2% air void. So this, so as for the content 5.4, we don't want beyond this as for the binder content. Beyond this, we're going to potentially have not just rotting issue, bleeding issue. And at the same time, if we choose again 5%, the lowest asphalt content is going to be 5.55. You can say 5.6. So with this range, and we're going to choose between 2% and 5%, we choose 3 asphalt content, 4.7, 5.0, 5.3. And the reason why we choose, plus minus 0.3, that's the construction tolerance in Texas. So that's why we choose 5, and plus minus 0.3. So after having these 3 asphalt content, we mold this, with this each specific asphalt content, we mold ideal rotting test specimen, ideal CT test specimen as short-term aging, this performance evaluation, and you got this curve. And this blue curve, that's the RT test result. You can see the higher asphalt content, you got the lower RT numbers. And for the right side, this orange line, that's the CT index, and the higher asphalt content, the better cracking resistance. And then, I remember this, we're using 65 as RT requirement, so that's the minimum. The highest asphalt content we can use, that's 5.24, and the CT requirement is 90, the minimum asphalt content is 5.1. So we have this balance zone, and for our this study, we choose 5.2 for the, we call balance asphalt content. For performance verification, that's the next step. For the performance verification, we use Hamburg test. We have 5.2 asphalt content. This is the test result. And for the result for the PG70 metal 22 binder is passing less than ½ inch, 5,000 passes. Just right here. A ½ inch is here. We're far below this number. So we pass Hamburg. For the ideal CT, after midterm aging, we got 55, it's larger than 40, so with a pass as well. So that's how we choose our asphalt content 5.2 for the field production. For this, then the QC/QA process, these are 3 control parameters. For lab mold density is 97.5. So how can we get the 97.5? Look here. I choose 5.2 here. This 5.2 asphalt content. You're going up. You got 97.5 just right here. So we're really, connecting our volumetric design information and also CT requirement for performance evaluation. The criteria 90, RT is 65. So this is a come up QC requirement. And here, that's the QC actual test result. And this acceptance criteria, the top line here and the bottom line here, that's the real what happened in the field. And the QC test, 97.5. And also we got the CT, or the actual number 99 and RT 75. So we're all good with the QC part. So this example showed how can we do from balance mix design and to the end of QC/QA requirement. So to sum up my presentation, and we really have a coherent framework established. We have two sets of lab tests. I do CT and RT for performance evaluation, the QC/QA, Hamburg, and I do CT for performance verification, and the midterm aging for cracking performance verification, and the short term for everything else. And it demonstrates this process. I want to quickly, acknowledge the work, the contributions from other people. And first of all, this presentation is developed based on a paper. It's published on the construction and building materials. This is the link you can get. This paper, get more detailed information. And also, appreciate the contribution from Richard Steger for longevity and the Professor Vola McGovern from University of Massachusetts at Dartmouth. Again, this presentation now reflects, official views or policy for any agency and supplier. And with that, I thank you for your attention. If you have any question, I will be happy to address. Thank you very much.
Thanks, Fuji. Well, we've got a few questions that were out in the chat. I tried to answer a couple of those, and then there's one or two that I probably didn't do right. But anyway, there's one question from Jason Bloomberg. He's asking, what's the specification for the ideal RT?
We do have the ASTM working. What was the name?
It's a draft. Yeah, it's a work item.
Yeah, we do have that, and if you're interested, I can send you the draft procedure.
Right. Yeah. So it's working its way through ASTM right now, through the D426 committee. Let's see. The next question is: I thought Ideal CT was has some issues with higher air voids testing. However, you said you run it at design air voids of 2.5 instead of 7.
Oh, I think I need to clarify for that. For performance tests, for performance evaluation or performance verification, we all mold specimen at 7% air void, 7 plus minus 0.5%. And when we choose the binder content, we choose the binder content corresponding to different air void. So that's two different things. One is when we talk about choose the binder content, we're talking about 2%, between 2% and 5% air void. That's only for choose binder content for performance evaluation. When you do the performance evaluation test, you mold all specimens at 7 plus minus 0.5% air void.
Okay. Thanks, Fuji. The next question or comment was sharing the link of the paper in the chat. And Caitlin, are we going to be able to send out the presentation slides, or will these be available?
Yep, they will be available on our Connecting the Dots website. So okay. It's through our behind the screen the blog. So they'll be available online and on YouTube on Longevity's Evotherm YouTube channel. Okay. And Mr. Park, if you want to, I'll put my email in there. If you want to send me an email, you can, I'll send you a copy of that, of the paper if you want. Let's see. Moving on to, can ideal CT RT be used with rubberized mixes?
I don't have that type of experience, but I think it should be okay. But I personally don't have much experience with that.
Yeah, I don't either. So that's a good question, Guadalupe. So we, I guess the short answer is we don't know. We'd have to actually run some mix through that. So it most likely it would, but we just have to run some tests. Let's see. Any other questions? Let's see. There was one at the very beginning that Mark Moyer asked, was about plant-produced materials for performance testing. Do you want to say anything about that, Fuji?
Plant produce mix during the production or after cool down reheating process. So that's different things.
Yeah, I wasn't exactly sure on that one. Mark, if you want to add a little bit more to that, maybe let me know. We can potentially answer that. Those of you that are interested in the RT specification, I'll put my email in there, and we can, if you can contact me, then I'll get you a link to the ASTM site so you can take a look at that. Are there any other questions in the chat? Don't see any more. One thing I was going to ask Fuji for you was on this framework. If users wanted to use something else besides the ideal CT, do you think this would work as well with the iFit and or the DCT? What would they need to do to adopt that procedure?
Oh, absolutely. You remember, we do recommend we have for performance verification, and we have DOT preferred test. They can use in any test they want to use. But specifically for the cracking side, you need to go through this aging process to generate your own mix with your own mix to come up with the acceptance criteria. So that's the only thing you need to do. Repeat the process to come up with your own specific criteria for specific cracking test. And we do have a step-by-step procedures, detailed information about midterm aging described in the paper. So you can reach out to me or Richard. We can send you the paper or the link, either way.
Right. So those of you that have my email or Fuji's email, just get in touch with us and we'll get you a copy of the paper. There's one other question from Blair Heptig with KDOT. He's asking, what temperature are you running the ideal RT? Is it 50 degrees C? Or
That's
is it
right.
room temp?
50 degrees Celsius. That's
50
because
degrees Celsius.
Yeah, RT is for rotting. We have to run at a high temperature.
Okay. Are there any other questions? Did I miss any? Probably did.
Perfect.
Okay, I think that's all the questions that we have, Caitlin. So
wonderful. Okay, well, like I mentioned before, thank you so much for presenting, Fuji, and we will send out the CEU credits via email. You can also find this recorded presentation on Evotherm's YouTube channel and on our blog site. If you have any additional questions, you can reach out to any three of us on this call as well. So thank you so much for joining.
thank you. Have a good day.
Thank you all.
Thanks, Fuji. Good job.
Thank you.